Hello, my name is Nikki Ballenhofer, as you see here. Today is April 26th, 2026. Pretty funny time to start. 2026. That's pretty funny. Anyways, so I'm going to be talking about my spread because I did an assignment for the or worksheet for spectral problem O. I'm in group 4 and this is my presentation. It's basically going to be talking about the spectral data and all the worksheet tables, these three, as you see here, and how I basically completed these to be able to lead up to the final structure, as you will see in the end. So, the first slide will be the molecular formula and degree of unsaturation. So, the molecular formula for this IR spectrum and everything else here is C6H12O2. And the degree of unsaturation, this formula will be 2 times of how many of the carbons plus 2 minus the total amount of hydrogens divided by 2. And as you see here, you get 12 plus 2 minus 12 divided by 2, and then you get 1. So this means that the structure either contains one ring, one double bond, or one double bond, which basically limits the like the possible structures that you will get in the end. So yeah, now we're going to be talking about the IR spectrum and its key peaks. So the first peak we have here, right here, uh, it's between 2,850 and 2,960 centimeters inverted. And that means we have a alkane carbon to hydrogen single bonded stretch. So for the second peak we have here is 1,740 centimeters inverted. And that here we would get an ester um, carbon double bonded to an O stretch. Excuse me. So, and then for this third one, this final peak, main peak we have here will be 1,200 centimeters inverted, which we will get a carbon to oxygen single bonded stretch. So together um, these three peaks are like important IR features that basically demonstrate that like the molecule contains like an ester functional group. So, the 13 carbon NMR. So we're gonna be talking about the chemical shifts and bonding environments. So if right here, which will be 171 ppm, which will be between these two, we will get an ester carbonyl carbon. And then all the way down here, we'll have 71 ppm. And this 71 ppm is basically a CH2 attached to oxygen. And then now here, for 28 ppm, we'll have a CH methane carbon. And for 21 here, we'll have methyl carbons adjacent to the carbonyl. And then for this last one here, we'll have 19 ppm, which is an isopropyl methyl carbon. So this next one here, we have a 1H NMR. So we have the H shift, integration, and multiplicity. So for this first one here, between 3 and 4, we have a 3.8 ppm, and that is a 2H doublet, which will lead to a CH single bonded to an oxygen, CH2 single bonded to an oxygen. Sorry. And then for the next one here, this tall one, which will be a 2.0 ppm, will be 3H. It would be a singlet because it's just one singular one here. And it would become a acetate methyl CH3. And then this one right here, this little multiple things right here, is a 1.9 ppm 1H multiplet, and that will become a methene CH. And then as for this final one, we have a zero point 0.9 ppm, and that's 6H here, and that's a doublet. And it's because you can see there's two peaks sticking out here, and that is two equivalent of a CH3 of an isobutyl group. So the partial structure reasoning, here we have like protons like splitting patterns in order to identify the isobutyl fragment. And while the 2.0 here, the 2.0 ppm singlet, it basically identifies like the acetate like fragment. It just helps it like identify it better. And all of these like fragments here or pieces, they all like connect through the oxygen in order to create like the full structure. And here is the final structure we have here, and this final structure is called a isobutyl acetate. As you can see, this structure here fits all of the data that we use to find this, which would be like the molecular formula, the degree of unsaturation, the IR structure, and the NMR evidence. So all of these are used in order to find this thing, the structure we have here called the isobutyl acetate. That is my video. Thank you so much for watching.